All right, how's everyone feeling today?
Totally awesome, sir.
All right, that's what I like to hear. So today we're going to first review how we fundamentally calculated electric field strength. And then we're going to look at what Biot-Savart did in terms of calculating magnetic field strengths in the same fundamental way. So on the left we have a line charge. A long linear line charge. It's positively charged. It has a charge density of lambda. And we're looking at a particular point P, which is a distance d from the line charge there. Now, we did a long drawn out derivation where we used a trig substitution to solve an integral to calculate the electric field strength of this particular point right above the line charge. And of course, the electric field at that particular point had a direction going up this way. And when we calculated the total electric field strength due to the whole shebang line charge, does anyone remember what we got? Griffin?
1 over 2 pi epsilon naught times the charge density lambda over d.
So this was for the whole shebang line charge. But the starting point for this, we looked at the contribution of each dq. And this particular dq over here, it would have a small contribution at point P. And James, what did we call dq's contribution to the whole electric field strength?
dE.
dE. And dE, due to that dq right there, would be going this way. But when we looked at symmetry and we went through the whole thing, what happened to all the x components of these little dE's? Kyle?
They canceled each other out.
They cancel each other out. So when push came to shove, what we wanted to do is calculate all of the DEYs. Now, what was an expression for each DE total right here in terms of the DQ? Evie?
KTQ over R squared.
And instead of saying K, I'm going to say 1 over 4 pi epsilon naught times DQ. What is it over, Evie?
Over R squared.
Or R squared. But when push came to shove, we know we really wanted to add up all the y components, and all the y components end up being equal to, well, you tell me. James?
That expression times sine theta.
Yeah, that expression times sine theta. 1 over 4 pi epsilon naught times dq over r squared times sine theta. This was our starting point. This was our starting point. And we added all these up. We integrated the DEYs, and then this was our final answer. All right, that's our little blast from the past. Now, let's look at what Biot-Savart did. Yes? Oh, where are this? The T's aren't pronounced, so it's Biot-Savart Law. Now, experimentally, experimentally, it was found that if you had a current carrying conductor and you came a distance d above this wire right here, at that particular point, point P, there was an invisible magnetic field around the current carrying conductor, and using the first right-hand rule for magnetic fields, what would be the direction of that invisible magnetic field at that point P above the wire? Evie?
It would be pointing outside of the page.
It would be pointing out of the page. If you grab the wire with your right hand, put your thumb in the direction of the current, we're going to have an invisible magnetic field coming out of the page right here and going into the page here. It makes like a circle, so it comes out of the page, goes into the page, around back, out like that. But we don't draw this circle like this. We can just draw the X and the O. So let me just backtrack here. And experimentally, it was found that the strength of this magnetic field, B, was equal to a certain expression. Does anyone recall that expression for the magnetic field above a current carrying wire? Kyle?
Is it mu naught over 2 pi times I over r?
I over D, right?
Oh, R over D in this case, yes. Thank you. Now, here's the genius of Biot-Savart. They had this answer experimentally, and then they worked backwards to figure out, hey, is there a fundamental inverse square law, kind of like the electric field one on the left? Is there an expression at this point P right here for the magnetic field not due to the whole shebang current, but just due to a little tiny piece of current? Like over here, we did it for a little tiny piece of charge, dq. Biot-Savart said, what if we break this long current up into little baby current elements? Now, what is a little baby current element? Well, Biot-Savart said that a little current element is equal to the current in the wire times an infinitely small piece of length of the wire, I dot dl. dl is an infinitely small little piece of length of the whole shebang length of wire. That little current element is going to contribute to the overall magnetic field up here at point P, coming out of the page. That little current element is a distance, whoopsie, let me get a different color here. R from point P. Now, guess what the current element's contribution to the whole shebang magnetic field is called?
dB.
dB. dB is the contribution to the whole magnetic field that came from the little baby current element right in here. Maybe I should highlight that. Well, remember how in the past we did that long, tough derivation and we went from here to there to get this answer? Biot-Savart had the answer, but they were trying to figure out, is there a corresponding relationship? Can we say that the magnetic field is due to a little piece of the current? And does it obey an inverse square law? So they did what we did before, backwards. They knew the answer, and they worked backwards to figure out what dB was. And this relationship that they got right here is known as the Biot-Savart Law. So, what is the relationship? Well, let me make a little room here. Mu sub naught over 4 pi times the current element I dot dl times sine of theta, where theta here is this angle right there between the direction of the current and that R value, all over. Anyone want to read your physics teacher's mind?
R squared.
R squared. It did obey an inverse square law.
Why did you use 4 pi in dB?
When Biot-Savart worked backwards and they started off with this,
Oh,
you ended up with a 4 pi back over here.
Where'd you get that current element from?
The current element is what Biot-Savart defined as like a little piece of current.
Okay, so what's the symbol for the current element? Just DI?
No, the current element is the current times dl. And there's no other name for it. It's the current times dl. That little thingamajig. You know, because they're kind of like pulling at straws here. They're trying to figure out, is there some kind of relationship between what we have over here on the right and what we have over here on the left? Over here on the left, what did we do with the whole charge? We broke it down into little pieces of charge, dq. What do we have on the right? We have this whole current. What did Biot-Savart say? Well, we're going to break this down, but the current is the same throughout. So what are we going to call each little piece of current? Well, they came up with this element called a current element, and the current element was IDL, the current in the wire, times a little tiny piece of the length of the wire. So here's a current element there, and then right next to it is another current element, and then right next to it is another current element, and then right next to it is another current element. And each one of those current elements contributes this much to the overall field. Now, I'm going to tell you right now, you guys are never going to be asked to use Biot-Savart where there's not at least a tiny bit of symmetry. You're never going to be asked to use Biot-Savart where the sine theta actually plays a role. It's always going to be every single current element piece is perpendicular, and it's always going to be sine of 90, which is 1. So after we take a short break, we're going to come back and we're going to practice using Biot-Savart.
What's the symbol for current element?
There is no symbol. It's just I.dl.